So last time we talked about if you have a position graph, what does the associated velocity graph look like? It gives you almost the same information. So now we're going to go the opposite direction. I have this first velocity graph here, and this tells me that this object is moving at a constant 10 meters per second for 15 seconds. So it's a constant velocity graph. Because the velocity is positive the whole time, it's always moving forward. And if I wanted to find the displacement, I could rearrange my average velocity function. V average equals delta x over delta t, cross multiply, delta x equals V average times delta t. So it's a constant 10 meters per second for 15 seconds. And I need to make this fit. We get 150 meters. That was easy. Now I've prepped another one here, and I want to do about the same thing. This thing starts off going at a forward constant velocity of 10 meters per second. Then it has a zero velocity, so it's stopped for 5 seconds. And then this object goes backwards for 5 seconds because we have a negative velocity. So we have constant forward, stopped, and constant backwards. It's just barely on the screen. I also want to look at what is the displacement. So we have 3 sections. So in the first section, we go at 10 meters per second for 5 seconds, so that's 50 meters. Second displacement, 0, because you're stopped. And then third displacement, we go -5 for 5 seconds. So -5 times 5, I'll go ahead and write this one out, is -25 meters. So overall, this displacement, 50 plus 0 plus -25, is positive 25 meters. Now I want to graph that. So the only piece of information this graph doesn't tell us is the starting point. So we are going to, in this case, assume the initial location is 0. And that is not what I did in the notes. Quick. It's supposed to be 10. Okay, so the initial location is positive 10 meters. So I'm going to end up moving forward 50 to 60, staying in the same place, and then moving backwards. So my associated graph here needs to go all the way up to 60 meters. So if I do it by 15s, I could do, let's do it here, x of m. So 60, 45, 30, 15, 5, 10, 15, because I'm trying to make the two graphs match each other. So this is 0, 15, 30, 45, 60, 5, 10, 15. So we initially start at the 10 meter mark, so it's about there. We go forward 50 and we get there by 5 seconds. So at 5 seconds plus 50, 10 plus 50 is 60. We stay there for the next 5 seconds. And then we go backwards, so back down the graph, 25. So 60 minus 25 is 35. So that's about here. How do we connect these points? Well, we know that a constant velocity, that's why we've got these funky stair-step things, because they were straight line here. Using the backwards thing, a constant velocity means a constant slope. Remember, velocity is the slope of a position graph. So constant velocity means straight line on position graph. And that works in either order. So I want to make these nice and straight. And just as a quick check on what I did, this description here, constant velocity forward because it was positive, stopped because the velocity is 0, and constant backward velocity because it's negative. That's what this graph shows too. Constant velocity because it's a straight line forward because it's a positive slope, stopped because we stay at the same location, and then constant velocity because it's a straight line, but backward because it's a negative slope. We did all that last year. We even graphed some of this last year. So the conversion we need to make is implied in the title of this. Way back up here, when we did 10 times 15, I want you to see that that's the area of a rectangle, okay? So the area of this rectangle, height of 10, width of 15, 10 times 15 is 150. If I did this here, I'd have two rectangles, really three, but the height of this one's 0, so I don't have to calculate that one. So I have a positive rectangle area and a negative rectangle area. The reason we do this is because now we're going to go to more generalized shapes. So slide the notebook up. Let's get to about there. And now I'm going to make a new velocity graph. 1, 2, 3, 4, 5. Time in seconds. This is 0, and we need to go 5, 10. Velocity in meters per second. But this object starts from rest, reaches a velocity of 10 meters per second in 3 seconds, and then goes back down to a velocity of 0 at 5 seconds. So this graph is showing speeding up because the velocity is increasing, and in the forward direction because they're positive numbers. In this section, the velocity is going from 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, all positive numbers. So it's a lesser and lesser velocity, but still positive. So this is slowing down, still forward. And the big question is here, what's the displacement? And I want a graph of it. So we're going to use this area idea. You want to break the graph into individual sections based on your changes in motion. So we have speeding up and slowing down, so we need to break this up into 2 triangles. We have a triangle there, and we have a triangle there. So again, we're doing area. So if this is a triangle, the area formula is 1/2 base times height. So 1/2, the base is 3 seconds, and the height is 10 meters per second. So 3 times 10 is 30, half of that is 15 meters. For our second one, again, it's a triangle, so 1/2 base times height. 1/2 times a base of 3 to 5 is 2 seconds, and a height, again, of 10 meters per second. So 20, half of that is 10 meters. So the overall displacement, because they're both 5, is 25 meters. And now we need to graph that, of course. So we are going to assume, for this more complicated one, assume that the initial position is 0. And again, try to match my time. 1, 2, 3, 4, 5. This is 0. Time in seconds. And I know I need to get to 25. 1, 2, 3, 4. I should have made that longer. Oh, let's just make it longer. 5, 10, 15, 20, 25. X in meters. So we start from 0. In the first 3 seconds, we went 15 meters. So 3 seconds to 15 meters. In the next 2 seconds, from 3 to 5, we went 10 meters. So I'm going to add on 10 meters, so that gets me to 25. Now we have the connection issue. This is not a constant velocity. This is an increasing velocity. Remember, a position graph's slope shows the velocity. So if I need my velocity to increase, I need my slope to increase. I don't use a straight line. I need a low slope, and then I need a steeper slope. So we call this an undercurve. And then we're slowing down. So we need to go from a high velocity to 0. So on this graph, a high slope down to 0. So this is an overcurve. So we're going to summarize these two assignments together. If you want to go from a position graph to a velocity graph, you look at slope. If you want to go from a velocity graph back to a position graph, you look at area. These velocity graphs that you get when you graph slope, it's often staircases. And the area graphs are often, but not always, curves, or they will include curves. We could have had in this problem here, increase in speed, keep a constant speed, then slow down. So we would have had an undercurve, a straight line for the constant velocity part, and then an overcurve. But you'll get to practice those in class today. So the slope of the position graph gives the velocity. The area of a velocity graph gives you back the position function. The same things also apply to acceleration. If you want to go from velocity to acceleration, you use slope. If you want to go from acceleration to velocity, you use area.